Now, yesterday we left off talking about fields, and I want to emphasize some points that'll hopefully make it a little easier to understand what I was getting at yesterday, because we were kind of rushed towards the end. But before we get to that, I just want to give you a visual as to why we know that charges tend to spread out evenly on the surfaces of conductors. That's something you want to know, you want to commit to memory. If you charge a conductor, i.e. a chunk of metal, the excess charge, not all the charge, because obviously you have metal atoms throughout the chunk of metal, and all those metal atoms hold on to a whole lot of electrons, but the excess charge is free to move around because of the whole electron sea that you learn about in chemistry, and those charges the excess charges will distribute on the surface. Now, if an object gets positively charged, then that means the electrons will leave the surface and leave a net positive charge on the surface. But it's easier to see if we have excess electrons. So imagine this is a three-dimensional sphere that we're looking at a cross-section of, and it's a solid sphere, and I've put some excess charge in the middle. Those excess negative charges all repel each other. So when I hit play here, ignore the ones that fly out. That charge immediately just gets distributed on the surface. In the case of actual conductors and actual electrons, it happens way faster than this. It happens very, very quickly, but you give this very rudimentary simulation enough time, and they will evenly distribute on the surface. Okay, and if you give it enough time, they'll actually be equidistant on the surface as well. And that carries important implications too that we'll see when we start talking about electric potential and voltage and all that stuff. So notice how they're pretty evenly distributed on the surface, right? And so anytime you put a charge on a conductor, that will be the case. If this is an insulator, that doesn't happen because the electric charge is not free to move. And so that electric charge just kind of gets stuck in place, and so it's not going to actually distribute on the surface of the insulator. And so you can imagine, though, and this is another way of looking at it, here you got a lot of electric potential energy, right? Just like when I lift an object up in the gravitational field, I store gravitational potential energy. If I take two charges and I move them together, I store electrical potential energy. So there's a lot of potential energy here. And nature is lazy. Nature likes to go to the minimum energy value, regardless of what you're talking about. That's why an object that's uphill will roll downhill, because it wants to move to a lower energy. So these charges, just by virtue of the fact that they feel the forces that make this happen, they want to go to a state of lower energy. But in an insulator, that doesn't happen. They're not free to do that. And so what's interesting is that you can actually store electrical energy within an insulator, because if you do charge an insulator or introduce electric fields within an insulator to get the charges to separate but not actually start flowing, then you can store energy in there. And that's the basics. That's the basis by which capacitors work, which are things that we'll learn about shortly. Okay. Now they're evenly distributed here, but if I have something like this, where it's not a uniform sphere, they're not going to be evenly distributed. And we're going to get into this a lot more in detail when we in a couple weeks here. But notice that if I have like corners, if I have a conductor that has edges and corners and stuff, they tend to congregate in the corners. And if you understand the forces involved here, each one of these little particles exerts a force on the other one, on all the other ones, then it should kind of make sense why they end up doing that. Okay.
Why don't they just disappear, like vanish?
What's that?
Why don't they just disappear?
The conductor itself?
One of the electrons.
If the electrons disappeared?
One of them did, yeah.
Oh, one of them. Then they'll move to do something that we'll talk about in a couple weeks. Okay, so that's what happens when you charge a conductor. When you charge a conductor, the electric charge moves to the surface. Regardless, notice that this is at the surface, right? Yes, there's some floating in there, but that's because electrons are very tiny. They don't occupy a lot of space, so they're gonna equilibrate on the surface in some way. Okay. All right, so I just want to go over that in the beginning here before we start talking a little more about fields. So I'm just continuing what we were talking about yesterday. And the take-home point yesterday was that the whole concept of a field is so that we can describe the physics, some type of physics, depending on what type of field we're talking about, we can describe a region of space. What could potentially go on or what is actually going on without having to take Logan's mass and put it there, right? So here I can say we're at the surface of the Earth. And we talked about yesterday how we can talk about G in terms of not just the acceleration due to gravity, but we can talk about it in terms of the strength of the gravitational field. We know there's a gravitational field that exists at every single point in space surrounding the Earth, because if I take my marker and I put it at any point in space and I drop it, it falls. Okay. And we know for years, even Logan and Mr. Henderson learned this last year, that the force of gravity is equal to mg. This is a vector equation, so the force vector is in line with the acceleration due to gravity, or now that we know, it's in line, in the same direction as the gravitational field. Okay. And then so we can write the gravitational field this way. It's the force of gravity on the object divided by the object's mass. And yesterday I told you that by doing this, we're talking about how much force per kilogram of mass you would expect to experience were you to put an object of that mass at some point within that field. Now let's talk about what I mean a little more in depth when it comes to what I just said. We want to truly understand that before we move on. So I know that the gravitational force, let me write it this way. Let me write the force of gravity is equal to mg. Right, let's just talk about the magnitudes for now. So just consider the magnitudes. Well, I also know that the force of gravity at the surface of the Earth is equal to big G times the mass of the Earth, this guy, times the mass of whatever object we put within the field. It could be a marker, could be Logan, could be this regulation size hockey puck. It could be any object that we put within the field. That's what this mass is. That's what that mass is. Divided by, in this case, the radius of the Earth squared. Now, if I look at the right two terms here, right, I just equate those two. Everybody brought little m to the party, and so you can divide it out. Because I can divide that quantity out, it has no bearing, right, on the result whenever I'm calculating the gravitational field strength, little g. And again, because we showed this way, the units for this are newtons per kilogram. So if I take a little object and I put it at this location, an object of mass m, it's going to feel a force of gravity that will be aligned within that field, with the field, with the gravitational field. And that gravitational force is due to that gravitational field. Right? We can think of it that way, at least. Obviously, space is not filled with an infinite number of little lines, but the field does exist at every point in space. If we are interested in a single point in space, then we just put that point into the mathematics, and then we can determine the field at that point, or the force on an object at that point. But notice that before I put that mass there is no force. Before I put that mass there's no force, there's just the field. But the field tells me that if I was to put a mass in the field, it would experience a certain force that I can calculate beforehand. Does that make sense? So if I know the field strength, then all I need to do is multiply that field strength by the mass in order to get the force using the equation that we've been using since you guys were 2 or 3 years old. Right? Does that make sense? So think about that whenever we move on, because this is stuff that, I know it's a new way of looking at gravity in terms of the things like gravitational fields, but that's not what this part of the class is all about. This part of the class is all about electricity and magnetism, and therefore electric fields and magnetic fields. So, where's the thing? Okay, yeah. So, you learned from the Mr. Fullerton's video that the electric field is defined to be the electric force acting on a charge divided by the charge in question. Okay? And so if I do the same thing, and the same kind of thing applies. I have the electric force. I can calculate the electric force on a charge just by multiplying the charge times the electric field. Right? Notice the units for the electric field are newtons per coulomb. Force is still in newtons, obviously. So if I know the field strength, then I can just multiply the charge by the field strength to get the force that acts on the charge, in the same way that we did with gravity just now. And so, just let me show you what I'm talking about here. There's too many things to juggle. I'm struggling. So I got another simulation up here. Those of you at home, I do apologize for the bright spot on the board, but I gotta be able to draw on it. Okay, so here, obviously, and let me make this guy stationary. I have a very large negative charge. Very, very large negative charge that I can think of as creating an electric field surrounding it. Okay? And as you learned, just by convention, we consider electric fields to point towards negative charges and away from positive charges. Think of like the gravitational field of the Earth. We consider the direction of the field to be pointing towards the mass, right? Because we have two different types of charges, we had to pick. Well, they had to point towards one and away from the other. And so by convention, they picked towards the negative, away from the positive. Okay. Specifically, they say that the electric field direction is defined in terms of what direction a small positive test charge would feel a force. So if I take a small positive test charge like this guy and put him within the field, it feels a force that way. That's the direction by convention that we call the electric field. Okay. If I move this guy around, obviously I get different electric forces depending on the different directions, different strengths depending on the location. So if this guy has charge big Q, and this guy has charge little q, then I can determine the electric field by just dividing the force that I can measure by the amount of charge. Not this guy's charge, but this guy's charge. And the reason that works is the same reason, that's not the light switch, is the same reason that the whole gravity thing worked. Because Coulomb's law is very much like the law of universal gravitation. So I know the electric force, according to that definition over there, is just the little charge times the electric field. And I also know, according to Coulomb's law, that that's 1 over 4 pi epsilon naught, which you can write k instead if you want, but this is how it's written on the formula sheet. So this is just like the proportionality constant times charge 1 times charge 2 over the distance between them squared. Well, if I equate these two, and let's just consider the magnitudes right now. If I consider these two, then the Q cancels, and look, the electric field is now defined, is now able to be calculated without actually having a charge there. Right? If I delete that charge, which I'll do in a second, the field still exists, but the charge isn't there anymore. But I can calculate the field by just taking Coulomb's constant, multiplying it by the amount of charge that's creating the field, right? That's this guy's charge. In the case of the gravitational field, it's times the mass of the large object, the Earth, divided by your distance from that object squared, from that charge squared. And so, if I delete this charge here, little q is no longer there, big Q is still here, the field still exists. I can calculate the field using this equation, and if you want, if you don't like writing 1 over 4 pi epsilon naught because it does get kind of tedious, you can just say, well, it's Coulomb's constant times the charge divided by the distance from the charge squared. Okay? So if I want to know the field strength here, I just measure r, the distance. I measure the amount of charge that's here, and then I throw it into that equation, and that's my electric field strength. Dan Fullerton went over this, but I just want to make sure you understand why this is important and why it's useful. Because it allows us to describe the physics of this space surrounding this charge without actually having to physically take a small charge and put it there and measure a force, right? The electric field tells us what force we would expect to have exert on a charge were we to actually place a charge within that space. But you don't actually have to have a charge in order for that to happen. Okay. That making sense? Kind of, sort of? Let me give you another visual, too. So this is on fet.colorado.edu. Last year, trying to remember last year when we used FET to do physics experiments. Notice that this is a positive 1 nanocoulomb, negative 1 nanocoulomb, because 1 coulomb is actually a huge amount of charge. Usually in high school physics labs and college physics labs, you're dealing with nanocoulombs of charge or microcoulombs of charge. But if I take a positive charge and put it there, those arrows indicate the field strength. And it is a vector field, so those indicate the electric field vectors or electric field lines. Notice they all point radially away from the charge. Now you could symbolize the strength of the electric field at each point by drawing a larger vector. Just understand that if you did that, these vectors would have to be really long. This one would be a little less long, then the shorter, and it would just fill up the whole thing with the ridiculous amount of electric field vector lines. So what this program does, there's different ways of dealing with that. What this one does is makes the smaller, the weaker electric field just less visible, right? More transparent. And so if I start adding more positive charge in the same location, then I get a stronger electric field, right? If I put a charge here, then the electric field starts getting a little more complicated. If I take a negative charge and put it here, now it starts getting that weird curvy shape that Logan talked about yesterday, right?
So hard.
And now notice that electric field lines always point away from positive charges and towards negative charges. Again, though, electric fields, the lines don't actually exist. The field is a thing. We describe that thing with a vector field, right? With a field of vectors surrounding whatever object is creating the field.
So the direction of the field, do the charges have like some kind of physical property that, we decided the positives go out and the negatives?
So the physical property is charge. Why do particles have charge? That's like asking why do particles have mass, right? There are very, very smart people that try to figure those kinds of questions out. I am definitely not one of them. But yeah, the way that we accept that this thing has mass, right? We accept that electrons have charge and protons have charge. And the direction of the field lines, not just the direction of the field lines, the naming of the proton as being the positive charge carrier and the electron, the negative charge carrier, purely by convention, right? That you could have just as easily said that the electron, the thing that's on the outside of the atom, could have been the positive charge and the protons could be the negative charge, and everything works exactly the same way.
Yeah, but the directions of the field vectors, like, is that just kind of like
that's also by convention. Yeah.
Oh, okay.
The direction of the fields were just decided. Okay, well, and really what they define the electric field direction as is if I took a small positive test charge, and this is arbitrary, right? I take a small positive test charge, I put it in the space, what direction does it feel a force? That's the direction of the field.
Okay.
But they could have picked a negative charge, but they didn't. They picked a positive charge. And so electric field lines could have pointed towards the positive and away from the negative, but that's just by convention.
Oh, okay.
And the physics works the same, regardless of which one you call positive, which one you call negative, which direction you define the electric field lines to point. It would work the same. You just got to be careful with your vectors to make sure you're being consistent with your directions.
Okay, that makes sense. That's what I was wondering.
Yep.
If you put a negative charge on top of a positive charge, it would just cancel it out.
Yeah. So you'd have to get it like, there you go. Yep. Very good. That's why objects with atoms with the same number of protons and electrons are neutral, right? Yep. Very good. Make sense? Cool beans?
Charge beams.
Oh boy. All right. Now, to calculate electric fields, Let me make sure I'm writing the correct thing. Yes. Yeah.
Is your camera plugged in?
It's plugged in, yes, thank you. Okay. This is what you have available, because you have to calculate electric fields. The current quest assignment has you calculating electric fields. So what is the easiest way to calculate an electric field? Well, you got to know, first of all, and this is what's written on the formula sheet. Tells you that the magnitude of the electric force is equal to 1 over 4 pi times epsilon naught. And again, you'll learn why that's a thing when we get into Gauss's law and some more complicated stuff. But this is also Coulomb's constant K, right? K is a way of abbreviating 1 over 4 pi times the permittivity of free space times the magnitude of the product of the two charges in question, just like with Newton's law of universal gravitation, the product of the two masses in question, divided by the distance separating them squared. So it's another inverse square relationship. And we're also given the equation, so this is needed. We're also given that the electric field is equal to the electric force divided by the unit of charge. So like I pointed, this is what you're given. In order to calculate the electric field, when you don't have a small q, you have to equate these two equations. Okay. And before I do that, let me just make sure, because we are given on the formula sheet, I'll put this in another color. On the formula sheet, we are given called the vacuum permittivity. It's epsilon naught, 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And then we're told that on the formula sheet, we get that K is equal to 1 over 4 pi epsilon naught, which is equal to 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. So that's what's on the formula sheet. So if you don't like writing 1 over 4 pi epsilon naught, now sometimes you're going to want to write that just to simplify things when we get to more complex stuff. But we can just rewrite the electric force equation as K, Q1, Q2 over R squared. Okay. Now, if we're dealing with a large charge, think of like the mass of the Earth and the mass of Gianni, right? The mass of the Earth significantly larger, and then the mass of Gianni pretty much insignificant in comparison. Well, usually that's what we're talking about when we're talking about calculating the electric field. We want to calculate the electric field surrounding a Van de Graaff generator. It's the thing that makes your hair stand up, right? You want to calculate that electric field. You got to relate it. You call that Q1 to some other charge Q2 that you might place in that field and then might feel a force because of the field. So we can just set these two or equate these two, rewrite this equation as the electric force is equal to the small charge, right, that's placed within the field times the electric field that is generated again by Q1, right? And maybe instead of Q1, Q2, I can write big Q, little q, in which case this is little q. This is the electric field generated by big Q. Does that make sense? You with me on that? You got to be with me on that. Okay. If we're talking about the electric force on the small charge, we want to know the electric force on this small charge. Well, we got to relate the force on that charge to the electric field in which it is residing. And that electric field is due to this larger charge, which is big Q in Coulomb's law. Make sense? Yeah.
So would that same force be acting on the negative particle?
Yes, yes. And I put the little thing there. There it is. So yes, that force does act on it. Yep. And in most situations, though, we know that the big charge isn't going to move. Like when we got the Van de Graaff generator up here, that thing that makes your hair stand up, when we turn it on, it gets charged very quickly, and it's not going to actually move when it starts exerting forces on the charges in your hair to make them stand up. Right. But yes, it does feel the force for sure by Newton's third law. right? Newton's third law is inescapable. 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 Yeah. I just turned that off because I know that this guy's stationary, and that's what we're interested in. Okay. So with these two equations, this guy would be big Q, this guy would be little q. And I want to know the value of the electric field at this point. Okay. To calculate that, I just set these two equations equal to each other. I just did this, but I'm doing it again because it's very important, and it's not on the formula sheet. I say the electric force, which is K big Q little q, over the distance separating these two charges. They're centers, by the way, is equal to little charge times the electric field. Again, what that allows us to do is cancel the little charge. So we don't even care about this guy. We want to describe that region of space, but we don't want to have to put anything there. Right? We want to be able to know that field strength without having to take a charge and put it there and measure the force that acts on it. So then we get the equation, well, the electric field is simply equal to K big Q over R squared.
Just realized something. That means since the force is dependent on how close it is, that means if you were to determine, like, say you have like two magnetic masses and how fast one would get to another, that would be complicated since the rate would be constant.
Oh yeah, for sure. We're talking about electric charges here, though. We're not talking about magnetism yet.
So maybe similar?
Yeah, similar. Yeah.
That's sort of what I was getting at.
Magnetism is, as you'll see, though, is significantly more complicated.
Oh no.
Yeah. Especially when you get into why magnetism arises, which has to do with relativity. That was Einstein's first major work, was explaining why electric charges create magnetic fields. And to do so required relativity. Yeah, it's interesting stuff. When we get to that we'll watch some videos on that.
Mr. Graham, is this possibly making electromagnetic pulse?
What do you mean by that? Like an EMP that could destroy the electrical system of the school or something?
I mean, not destroy it, just accidentally hinder the function of.
Something about
If you want to maybe do that for a project, you know?
Just your camera, that's it.
Detonated in school.
Just your camera.
Okay, so I can't emphasize this enough. That's important. That equation, the electric field is equal to K times the charge that's responsible for the field divided by the distance from that charge squared. That gives you the strength of the electric field at whatever location that happens to be. If you wanted to be nitty-gritty about the vectors, remember that R is not just a distance. For big kids, R is a position vector. Right? And so if R is that way, and this is, I should have done this. Let's pretend this is a positive. Never mind. Because the electric field actually points away, right? So I'm sorry. I don't want to put too much at you now. Use that equation to calculate the field strength, and then whether it's pointing towards, or whether it's due to a positive charge, it will be pointing away from the positive charge. If it's due to a negative charge, it'll be pointing towards a negative charge. So you can use your vectors in that way. Okay, so that's why you're given this, the magnitude, right? And then you have to decide whether the force and the field point towards or away. The force always points in the same direction as the field. So remember that. Okay? All right. So you watched the video from Dan Fullerton where I actually went over some example problems with this stuff. Understand that the principle of superposition is going to be huge for us. Did he mentioned superposition, right? If he didn't, he did so indirectly. Superposition, when we studied waves we didn't even get to waves, did we?
No, we didn't.
We didn't get to waves last year.
I remember learning about it.
When you have two waves interact, they actually constructively interfere when they're in the same space and they grow larger. We should have done a little
Like
bit
in
of
the
that.
ocean.
Like in the exactly. I remember riding boogie boards because I grew up in Southern California. And if you find regions of the beach where the two waves come together and you ride one of the waves, whenever you hit the other one, sometimes it'll just shoot you up into the air because the waves will literally just add. So you say that superposition of those waves adds up to a larger wave. Okay, so if I have a charge here, a positive charge here, and a positive charge here, well, and say this is charge A, this is charge B. Well, let's say at this point in space, I have a field due to charge A, so I could say that's electric field due to charge A, and it points radially away from the charge, and then charge B creates a field that points this way. The net electric field is the vector sum of those two electric field vectors. So the net electric field would point, you would have to add, and to do this rigorously, you would have to decompose these into the x and y components, then add the x components, add the y components, and then do Pythagorean theorem to figure out the hypotenuse. But long story short, that ends up being the net electric field. So electric fields obey the principle of superposition, which means if you have multiple electric fields existing within space, you have to add their effects in order to get the net electric field. Yeah.
This is assuming that the particles are not moving?
Yes.
Okay.
Because if they are moving, then the electric field will be changing.
Yeah.
And then it's too
Bounce
much
away
away.
from you.
All right, so is all that kind of making sense a little bit?
Yes.
You guys started on the quest assignment?
Yes. A little bit.
I have a question on the quest assignment for paper.
If what?
I have a question about the quest assignment.
Okay, shoot.
It's the one with like you have
So it's 50 different steps too.
it's like you bring over the negative charge, you bring them apart, you put them together, you ground it, you take it apart, you put away the negative charge. It's like a whole.
Number 10. We got the
Yeah.
answer, but we just want to know why.
Yeah, it's like the whole grounding part. I think is more.
Okay.
Because Dan Thorson briefly brought it up, but like in a
Yeah.
yeah, you know what I mean.
And I
Okay.
think it was Y and X.
So two uncharged metal balls, Y and X, each stand a glass rod and are touching, so they're insulated from the ground. A third ball carrying a positive charge is brought near the first two. So positive charge is brought to here. While the positions of these balls are fixed, ball Y is connected to the ground.
That's a negative charge for the. Yeah.
Okay. So what happens in X and Y, these guys are in contact and they're conductors. Electrons will flow off of this guy because they're repelled by these electrons. And so we end up with a net negative charge on this guy and a net positive charge on this guy. Right? It's like separation of charges like in the wall with the balloon, but the charges are actually free to move. And so they move over to this way. These electrons want to get as far away from that negative charge as possible. So then we ground it. Let me read this real quick. Yeah. And so then we ground, use blue for a ground wire. That's the schematic for a ground wire. So ball Y is connected to the ground. These electrons are now free to move away from this charge, right? So these electrons will now leave. So those electrons are now in the ground, okay? Leaving us, and then we bring the other guy away. Then we disconnect the ground wire. And there's still, yeah, disconnect the ground wire. While they remain in touch, the ball carrying the positive charge is now removed. So we remove this guy. And what were positive charges here will now redistribute within, right?
Okay, that makes sense. So it just distributes then the charge.
Yeah.
From one wall.
Yeah, and so if you were to consider this to be a single object, it then, and it's not the positive charges that flow, but it's excess, it's electrons over here that are feeling the attraction of those. So electrons will leave this ball, and so you get a positive charge there, and then you disconnect them, and now they're both positive.
Okay.
And if you have a different problem where instead of a negative charge gets brought in, a positive charge gets brought in, you end up with the exact opposite.
That made it a whole lot easier.
Cool. Oh, this mask today. What is the deal? Okay. We will be working on that quest assignment on Monday, by the way. Okay.
Oh, okay.
I changed the due date to Monday night. Because there was something I want to talk about real quick today, just to emphasize why it's so important. Look, because these are 4 equations that are on your formula sheet. Okay, and they're ones that I want to show you now and tell you that these are the ones. If you've looked at the formula sheet, these are Maxwell's equations. The first Maxwell equation we come to will be this. It's an integral equation. So we've talked about a couple of these things. We've talked about electric fields. We've talked about charge. We've talked about the permittivity of free space. This is an integral symbol. I'm just pointing this out now so when we get to it, you're like, oh, remember that. This circle means over the integral over a closed surface. This is called Gauss's law. You guys heard of Gauss?
Yeah, I think so.
Anyone taking statistics?
Yeah, I think statistics. There was
Gaussian curves,
the normal distribution.
normal distribution.
Oh.
Yeah, Gauss did that too. Gauss is one of the giants in the realm of not only physics but mathematics as well. He essentially invented statistics.
There's also a Gaussian blur in photo editing. I don't know why that's named after him. But
Yeah, I have no idea.
Gauss can.
So that's Gauss's law. Closed surface means I actually have to do 3-dimensional stuff in order to determine this. In this class, those closed surfaces are going to be symmetrical, so it's actually not going to be difficult. In fact, when we use this, and I try to point this out because I remember struggling with this. But when you first learn this kind of stuff, the hardest part of most problems where you have to use Gauss's law is determining how much charge is present at the location. This integral you'll be able to do in your head most of the time. Okay, because it's just going to literally be dA is an area. dA is an area vector that represents a small section of area. And so you add up all the area vectors and it makes a sphere. So it's really easy. So I'm just pointing this out because it's not going to be that difficult. I just want you to show what the culmination of this part of the class is leading to. And that's the 4 Maxwell's equations. So what this tells you is that the integral of the electric field dotted with these dA vectors, which essentially just means the amount of electric fields that are passing through a surface, a closed surface, is directly proportional to the amount of charge within that surface. Okay. And that's inversely proportional to the permittivity of free space. The easiest of Maxwell's equations has to do with magnetic fields, because magnetism starts with the letter B. The magnetic field gets the symbol capital B. And if we are integrating over a closed surface, then that is always 0. What this means is how many electric field lines are either passing out of or into a closed surface. How many magnetic field lines are pointing into or out of a closed surface. It's always 0 with magnetism because anytime you have a magnet, you have field lines going from one part of the magnet and then into the other part of the magnet, right? So there's no surface you can draw, with no closed surface you can draw anywhere around that magnet where you have a net influx or a net outflux of magnetic field lines. It's impossible. And so you can think of, you might have heard of this before, there's literally no such thing as a magnetic monopole, at least as far as we know. Some versions of string theory, for reasons that I definitely don't understand, predict the existence of what they call magnetic monopoles. But if this is true in all cases, then you can't have an isolated north pole of a magnet or south pole of a magnet. So that's in words, the information that you can actually get out of this equation. And because it looks like this one, and because Gauss did that too, that's Gauss's law
2.0.
for magnetism, or 2.0, yeah. The third Maxwell equation, and actually I'm not going to get too much into it. The third Maxwell equation on the formula sheet is Ampere's law, where we have another closed thingy, but this is a closed loop. Now we're talking electric circuits. This is like a closed electrically conductive loop of wire or something. And the integral is going to be of B, and on the formula sheet it's B dot dl, and that just means a differential length of a wire, usually. That's what it is. That's equal to it's like the magnetic equivalent of epsilon naught, but it's the permeability of free space, or the magnetic permeability it's called. It has to do with magnetic field lines within space, times the electric current that's actually traveling through that loop of wire. Okay, that's Ampere's law.
It's almost like we got ink from his name.
Yeah. I wonder if that's true. And then we culminate at the end of the class with, how's it written on the formula sheet? With Faraday's law, which says that the induced EMF, you might have heard of EMF, it's the electromotive force, which is not a force. That's a misnomer, unfortunately, but the name stuck. It's the induced voltage, or the induced electric potential difference, is equal to the integral, and the reason this is the culmination, you'll see in a second, of the electric field dotted with dl. Again, electric fields in a part of a wire that has electric current running through it, and that's also equal to the negative derivative with respect to time of the integral of B dot dA. Now this right here is a closed loop. Notice no circle there. This is an integral over what we call an open surface. And the reason I'm pointing this out is when I struggle with this a lot. And I wasn't told at the beginning of class when we started learning about this that it's not as bad as it looks. If you can understand, but if you understand Maxwell's equations at a very high level, you literally don't need any other formulas. You can get anywhere in the realm of electromagnetism with these four equations. Why are they called? This is Faraday's law, by the way. Why are they called Maxwell's equations? That's interesting, right? Faraday's. And this one right here looks super complicated, and it kind of is. But look what it relates. It relates an electric field to a changing magnetic field. It relates the magnetic field to an electric field. Electromagnetism. Right? How do you get magnetic fields produced? You have to have an electric current. Right? And then a changing magnetic field can then induce an electric field. Right? You have a magnetic field that's changing with respect to time, you get an electric field produced. And then that electric field will in turn produce a changing magnetic field. And so you get, if you ever look at an electromagnetic radiation, at least a visual schematic of it, you have magnetic fields oscillating in this direction and electric fields oscillating in a perpendicular direction.
Does that have like AC power over it?
Kinda. The electromagnetic radiation is light though, right? So it's kind of different.
But it's not like if you like have a motor or something and you turn it and it produces it.
Yeah. How does you ever watch Breaking Bad? You did?
Yeah.
Remember whenever the RV broke down in the desert and they had to crank the thing to get the RV? Yeah. When you're cranking the thing, you're moving a magnet through a coil of wire. That moving magnet induces a changing electric current. Or it induces an electric current within the wire. Right? Yeah. Now, let me finish this with, when you're in college, and just so you know, in this class, when we use these, we're going to have a high degree of symmetry. And the symmetry makes the integrals very easy to do. The integrals actually aren't very difficult in the problems that we do here. Eventually, you get to the point where, okay, now we can do more complicated stuff. But what's interesting is that Maxwell took these four laws, which are not named after him, did a lot of hardcore vector calculus, and discovered that when you combine these equations and you recast them in a certain way, you get an equation, a differential equation, that literally matches the known differential equation that described wave motion. People knew when Maxwell figured this out that there's an equation that is a function of position and time that would describe, say, the motion of a wave on a stream or water waves in water, right? The same differential equation will describe any type of wave. You can recast these four equations, and this is what Maxwell did with Heaviside. They did this and realized that, these equations describe waves. Those waves we now know are light. Those are electromagnetic waves. And you can recast these equations and then figure out that the speed of these waves should be equal to 1 over the square root of these two constants multiplied together. And it turns out that that speed is about 3 times 10 to the 8th meters per second. And then a guy named Ole Romer came along a few years later and used a very ingenious experiment to measure the speed of light. And guess what the speed of light ended up being? That speed. And so the speed of light is literally that, which you can get from the four Maxwell's equations. It's cool stuff, guys. This is cool stuff. We're going to start with, this is the first one we'll see. This one's really easy. We barely use it at all. You just want to understand what it means conceptually. When we start doing circuits, we'll start dealing with this one. And then we'll tie it all together at the end with this. We don't get to the differential equation that ties it all together. These are the integral versions of these equations. There's differential versions as well, but we don't deal with those because they involve vector calculus and that upside down triangle that you might have seen if you've looked at vector calculus stuff. But anyway, it's good stuff, guys. This is fun stuff.
Is like a partial derivative kind of like a circle integral?
No.
Okay.
Partial derivatives, instead of d dt, like partial derivative with respect to time, it looks like a weird looking d.